Chapter 11.7, Events Involving and Conditional Probability. Two events are independent events if the occurrence of either of them has no effect on the probability of the other. For example, consider tossing a fair coin 2 times in succession. The outcome of the first toss, heads or tails, does not affect what happens when you toss the coin a second time. The occurrence of tails on the first toss does not make tails more likely or less likely to occur on the second toss. The repeated toss of a coin produces independent events because the outcome of one toss does not affect the outcome of others. Mutually exclusive events cannot occur at the same time. Independent events have no effect on each other. So in general, if two events are independent, here's the formula for their probability, right? We're going to multiply the probability of the first one times the probability of the second one. The AND rule, right? This is for an AND probability, can be extended to cover 3 or more independent events. In other words, the probability of A and B and C is the probability of A times the probability of B times the probability of C, and that can be extended. Okay, let's look at the probability of a baby girl. So the probability of a baby girl being born is 1/2, right? The probability of 9 girls in a row then would be, what's the probability that you get a girl and a girl and a girl and a girl? Let's change that from 9 girls in a row to 1, 2, 3, 4 girls in a row, right? So it's just the probability of getting a girl times the probability of getting a girl times the probability of getting a girl times the probability of getting a girl, because these events are independent. Whether you have a boy or a girl the first time does not affect whether you're going to have a boy or a girl the next time. So 1 out of 2 times 2 is 4, times 2 is 8, times 2 is 16. The probability of having 4 girls in a row is 1 out of 16. And if another child is born to the family, the event is independent, so the probability of a girl for their next child is still just 1/2. Two events are dependent events if the occurrence of one of them has an effect on the probability of the other. So if A and B are independent events, here's our formula. It's an AND probability still, but it's the probability of A times not just the probability of B, but the probability of B given that A has occurred. For example, let's say you're eating out of a box of candy, and let's say there's 3 pieces of chocolate in the box and 2 butterscotch and 1 cherry. And you want to know what's the probability that you eat a butterscotch and then a cherry? Well, it's the probability that you get a butterscotch. So 2 out of 3, 4, 5, 6 times the probability that you get a cherry given that you've already eaten a butterscotch. So there's still 1 cherry, but now there's only 3, 4, 5 choices to choose from. Or, if we reduce this to 1/3, 1/15. Okay, so notice mutually exclusive is we're concerned with events being mutually exclusive when we're dealing with or probabilities. We're concerned with events being independent when we're dealing with and probabilities. Now we've got the probability of an event happening at least once. Okay, the probability of an event happening at least once is 1 minus the probability that the event does not happen. A lot of times it's very difficult to calculate the probability of an event happening at least once, because let's say, well, here's as an example, I guess. Let's just go ahead and use this. If the probability that South Florida will be hit by a hurricane in any single year is 5/19, what is the probability that South Florida will be hit by a hurricane at least once in the next 4 years? Okay? To calculate the probability of being hit at least once, if we did it without this notion up here, then we would have to find the probability that South Florida is hit by a hurricane once in the next 4 years, plus the probability that it's hit twice, plus the probability that it's hit 3 times, plus the probability that it's hit 4 times. So generally, it's easier to figure out what's the probability that it's not hit at all. So let's do that. Let's find the probability that it's not hit in the next 4 years, right? So that would be the probability that it's not hit by a hurricane, and that it's not hit by a hurricane, and that it's not hit by a hurricane, and that it's not hit by a hurricane. Now these events are independent. So if the probability that it is hit by a hurricane is 5/19, remember the probability that it's not hit by a hurricane is 1 minus 5/19, or 14/19. Now if I'm doing an and probability and they're independent, then that's just the probability that it's not hit the first year, and it's not hit the second year, and it's not hit the third year, and it's not hit the fourth year. All right, let me grab my calculator, see what that is. So that's 38,416 over 130,321. Okay. So now we want the probability that it's going to be hit at least once. Well, this is the probability that it's not hit at all, right? So that means every other combination that adds up to 1 will mean it's hit at least 1. That would count hit when it's hit 1 year, when it's hit 2 years, when it's hit 3 years, when it's hit 4 years. So the probability that it's hit by a hurricane at least once is 1 minus this right here. And it's probably going to ask you to round this to, let's say, 4 decimal places. So I'm just going to punch that in my calculator. to get point, and if we're going to round to 4 decimal places, 0.7052. So a little more than 70% chance that South Florida will be hit by a hurricane at least one time in the next 4 years if the probability of it being hit in any single year is 5/19. Okay, so at least one probability. And we'll do some more examples of that when we get to the question section. Okay, so we've seen that for any two events, any two dependent events, that the probability of A and B is the probability of A times the probability of B, given that A occurs. That's called a conditional probability. The probability of B, given that A occurs, is a conditional probability. And here's a formula to calculate that. Okay, notice this is simply the number of outcomes common to B and A, and this is the number of outcomes in A. Be careful though, because the probability of B given A is not the same as the probability of A given B. Let's look at an example. You're dealt one card from a 52 card deck. Find the probability of getting a heart, given that you were dealt a red card. Okay, now I'm going to plug into the formula, but just like odds, we're going to make a comment about we may not need to specifically use the formula every time. So here's my formula. I need to know the number of cards that is a heart and red. Okay, that is a heart and red. How many cards are hearts and red? All of them, right? All of the hearts are red. Over the number that are red. How many are red? 26. So 1/2. Okay, that's plugging into the formula. But think about this. Find the probability of getting a heart, given that the card you were dealt is a red card. If you know the card you were dealt was a red card, then you automatically know you're only talking about using 26 cards of the deck. So what's the probability the card is a heart out of red? 13 out of 26, right? There are 13 of the red cards that are hearts. What about this? Find the probability of getting a red card, probability that it's red, given that the card you were dealt is a heart. Again, plugging into the formula, I need to know how many cards are red and hearts. That's 13. And this time, I need to know how many are hearts. That's 13. Right? 1. What's the probability of getting a red card given that you were dealt a heart? 100% chance. If you know the card you've got is a heart, 100% chance that it's red. All the hearts are red. Okay, let's look at how we can apply these ideas. You have a spinner with 6 equally sized sectors. There are 3 red, 2 green, and 1 yellow. So let's kind of, now pardon my drawing here, 6 equally sized sectors. Let's see if we can get an idea of what it looks like. We've got 3 red, let's just do our 3 red like this, 2 green, and 1 yellow, just to get us a visual here. Okay, it's equally probable that the pointer will land on any one of the 6 regions. If the pointer lands on a borderline, spin again. So if the pointer is spun twice, find the probability that it will land on a green and then a red. Green and red. Now again, notice this is if the pointer is spun twice. If the pointer is spun once, the probability it's going to land on a green and a red is 0. None of these are green and red simultaneously at the same time. So pay attention to whether you're talking about one draw, one spin, or 2 or 3. So the probability it's going to land on a green and a red. These events are independent. One spin has no effect on the other spin. So it's simply the probability it's going to land on green times the probability it's going to land on red. The probability it's going to land on green, well, there are 2 out of 6 regions that are green. And the probability it's going to land on red, there are 3 out of 6 regions that are red. So if I simplify these, it's easier to simplify these in the problem than when your numbers are larger. This would be what, 1/3 times 1/2 or 1/6. If the pointer is spun 3 times, find the probability it will land on green and then red and then yellow. So the probability it's green and red and then yellow, they're still independent. So it's the probability it lands on green, 2 out of 6, times the probability it lands on red, 3 out of 6, times the probability it lands on yellow, 1 out of 6. Or, let's just do this. This 6 will cancel this 6, right? 1 out of 36. What's the probability to land on red every time? Well, that's the probability that it's red, and it's red, and it's red. So the probability it lands on red is 3 out of 6. Or let's go ahead and make that 1/2, since I know that every one of these is going to be 1/2. A single die is rolled twice. Find the probability of rolling an even number the first time and a number greater than 2 the second time. Okay, it's rolled twice. So the probability that we have an even number and a number greater than 2. These events are independent, right? One roll has nothing to do with the first row. So the probability it's even, 2, 4, or 6, there are 3 even numbers out of a 6-sided die. That's the probability it's even, times the probability your number is greater than 2, 3, 4, 5, 6. There are 4 ways to get a number greater than 2. So again, if we're going to reduce these fractions, just so I don't mark a bunch of stuff up, I'm going to go ahead and make this 1/2, 2/3, and then we can mark it a little bit up to make it 1/3. You draw one card from a 52 card deck. Then the card is replaced in the deck shuffled, and you draw again. Find the probability of drawing a face card the first time and a heart the second. So the probability that you get a face card and a heart. Now, I have to figure out if these events are independent. And because the card is replaced, then they're independent. So all I have to do is find the probability of getting a face card. Well, there's a Jack, Queen, King of every suit. So 3 times 4, there's 12 face cards out of the 52 cards. And then how many are hearts? There's 13 cards that are hearts out of the 52. And again, if we simplify this, these are both divisible by 4. So I get 3 13ths times 1/4, or 3 52nds. Okay, find the probability of drawing a black card each time. Well, again, we put that card back in, so these events are independent. A black card, half of them are black, right? 1/4. But think about this. Answer the questions above if you do not replace the card back into the deck, but simply draw another card. Ah, no longer independent. These are now dependent events. You have changed the probability of that second event. So in this case, it's the probability of drawing a face card from a full deck. That's still the same. But now you have to consider that you have drawn a face card. So your hearts, how many hearts? Now this is, oh, this is a poor example. Sorry for that. I'm going to ignore this fact. If some of you have a question about that, you can call me. But I'm going to ignore what makes this an example. Unless some of you catch it, call me and we'll talk about it. Okay, so how many cards are hearts? 13, but there are only 51 cards left that you're drawing out of, right? Completely changes the probability of that second one. So if we simplify this now, this will simplify to 3/13, but this is not going to simplify to 13 over 51. So 3 out of 51. What about this one? The probability that you draw 2 black cards in a row without replacement. The first one is the same, 1/2. I'm going to change this back to our 26 out of 52 instead of 1/2. But now I have to consider the fact that I have drawn a black card. So that means there's only 25 black cards left out of 51 total cards. So then in this case, I still have the 1/2, but then 25 over 51 does not simplify, giving me 25 out of 102. Okay, so the difference between, sometimes you call this with replacement and without replacement, which changes whether it's independent or dependent events. Okay, there are 30 chocolates in a box, all identically shaped. 5 are filled with coconut, 10 with caramel, whichever, and 15 are solid chocolate. You randomly select one piece, eat it, and then select a second piece. Find the probability of selecting 2 solid chocolates in a row. Well, if you choose one and eat it, you have changed the probability of that second one you're going to get because you've changed the number of chocolates in the box. So these are dependent events. So we have coconut, caramel, chocolate. Okay, 2 chocolates in a row. So let's do CH and CH. Okay, the solid chocolate, the probability your first one is a solid chocolate. There's 15 solid chocolates out of the 30. But if you eat one of them, now there are only 29 chocolates left in the box. And not only that, but there are only 14 solid chocolates. So the probability of that second one you select being another solid chocolate has changed to 14 out of 29. So let's change these probabilities. Let's simplify that one to 1/2. And then that makes this easily simplified. 7 out of 29. All right, what's the probability of selecting a coconut? So a coconut and a caramel. Well, the probability of getting a coconut, there's 5 coconut out of 30. But once you eat a chocolate, there's only 29 left. Now, all the caramels are left, so there's still 10 caramels. And then just simply simplify. So 5, 87, 5 87ths. The numbered discs shown are placed in a box, and one disc is selected at random. Find the probability of selecting a 3 given that a red disc is selected. Now we've got a formula for this, but again, remember the way I can think about this. Hey, if I know that disc is red, the only ones I'm considering are the red disc. I know it's red. So what's the probability of getting a 3 out of the red disc? 1 out of 1, 2, 3, 4, 5. 1/5. Okay, I could plug into the formula, or I could just kind of understand what that means. What's the probability of getting an even number given that a green disc is selected? Well, if I know the disc is green, then I'm only talking about out of 3, right? So how many of them are even of the green discs? 2 out of 3. Okay. Let's see, what's the probability that it's red given that an odd number is selected? All right, well, so if it's odd, I've either chosen the 1, the 3, the 5, or the 7. So 1, 2, 3, 4. How many of those 4 are red? 3. Find the probability of selecting a red disc given that the number selected is at least 5. Greater than or equal is our mathematical representation of at least 5. Well, if it's at least 5, right, then that's one of these discs. And what's the probability it's red out of these discs? 3 out of 4. Okay, that wraps up 11.7. Good luck. Have fun.